In this video, we will look at graph isomorphisms. Now take a look at these two graphs. After close examination, we can see that these are actually the exact same graph. They have the same vertex set and the same edge set. Furthermore, their edge endpoint functions are exactly the same. If we now look at these two graphs, these two are different graphs, right? So we can see the graph on the left here. The endpoints of E1 are V1 and V3, versus here the endpoints are V1 and V2. However, it is undeniable that these two graphs are similar. In fact, a simple relabeling of the vertices and edges of the right graph, this one over here, will give us this graph over here. This is what we mean when we say two graphs are isomorphic. They have similar properties. So formally, let G and G prime be graphs with vex sets V of G and V of G prime, and edge sets E of G and E of G prime, respectively. We say that G is isomorphic to G prime if and only if there exists one-to-one correspondences, nu. So this here is the Greek letter nu, is a function from V of G to V of G prime, and epsilon, right? So this is the Greek letter epsilon, is a function from E of G to E of G prime, such that nu is an endpoint, such that V is an endpoint of E if and only if for each V in V of G and E in E of G, V is an endpoint of E if and only if nu of V is an endpoint of epsilon of E. So we wish to show that these two graphs are isomorphic. So what we have to do is we have to find one-to-one correspondences, one from the vertex set of this graph to the vertex set of this graph, and one from the edge set of this graph to the edge set of this graph, such that for all V in the vertex set here, and for all E in the edge set here, V is an endpoint of E if and only if nu of V is an endpoint of epsilon of E over here. Now, this is partly a matter of trial and error and partly a matter of deduction. Now, first, let's go ahead and notice that E2 and E3 are parallel. What this means then, and I'm going to go over to the next slide for right now, is that epsilon of E2 must be parallel to epsilon of E3. Well, if we look back over here, F1 and F2 are parallel. So one of these two will have to be F1 and the other one will have to be F2. Let's say that epsilon of E2 is F1 and epsilon of E3 is F2. Now the endpoints must correspond. So the points are V3 and V4. In G prime, they're W1 and W5. So V3 will have to go to W1 or W5, and then V4 will go to the other one. So let's say that nu of V3 is W1, and we'll say that nu of V4 is W5. All right, so that at least takes care of two edges and two endpoints. Now notice here that V1 has four edges. Right? It has E1, E4, E7, and E5. So nu of V1 must also have four edges. So we look here, we look over in G prime, well, the only vertex that has four edges is W2. So nu of V1 must be W2. And of course, all the edges must correspond. So E1 we can say is F3. E4 we can say is F4. E5 we can say is F6. And E7 we can say is F7. We said that was going to be F3. I think it was E4. E4 will be F4. E5 is F6. And epsilon of E7 is F7. And we have to continue in this way. Doing so, we can get two one-to-one correspondences. Okay, let's say this is, I don't know if that'll be large enough. Let's say this represents V of G. We'll say this represents V of G prime. Right, we're going to have our one-to-one correspondence nu. We have how many vertices? 1, 2, 3, 4, looks like 5 total vertices. On either side. Now from above, we already know that V3 will go to, I'm sorry, these should have all been W's, not S. I don't know why I wrote S. Now V1, or V3 goes to W1. V4 goes to W5. We had V1 going to W2. That leaves us now with V2 and V5. We can send V2 to W3. V2 to W3. And then V5 would go to W4 by process of elimination. And V5 to W4. And we can verify they do have to be connected by an edge, and they are. Now let's look at E of G and E of G prime with our correspondence epsilon. How many edges do we have? We have a total of, it looks like 1, 2, 3, 4, 5, 6, 7 edges. These are where the F's go. All right, now we know that E2 will go to F1, E3 will go to F2, and E1 goes to F3, E4 goes to F4, E5 goes to F6, and E7 goes to F7. So that leaves us with E6, and E6 must go to F4. No, I'm sorry, E6 must go to F5 by process of elimination. And again, we can confirm this. If we look over here, E6 has to connect V5 and V2. Right, now we said V5 was W4, V2 was W3. So that means that F5 must connect them, and it does. So here we go. Here is our one-to-one correspondences. This proves that G and G prime are isomorphic. Now let S be a set of graphs and let R be the relation of graph isomorphisms on S. Then R is an equivalence relation on S. So recall that to prove an equivalence relation, you have to prove the relation is reflexive, symmetric, and transitive. So for reflexivity, given any graph G and S, define a graph isomorphism phi from G to G by using the identity functions on the set of vertices and on the set of edges. So this phi is essentially acting as a set of two functions, nu and epsilon. Now again, remember, nu goes from V to V, epsilon goes from E to E. Well, that's symmetric, right? G is isomorphic to itself. That's all we had to do was find those one-to-one correspondences. For symmetry, given any graphs G and G prime and S such that G is isomorphic to G prime, we must show that G prime is isomorphic to G. Now, since G is isomorphic to G prime, we know that there's going to exist two one-to-one correspondences, nu from V of G to V of G prime, and epsilon from E of G to E of G prime, that are one-to-one correspondences. Well, then there are one-to-one correspondences, nu inverse from V of G prime to V of G, and epsilon inverse from E of G prime to E of G, which preserve the endpoint functions, the edge endpoint functions. Thus, G prime is isomorphic to G, right? That's what we had to do. We had to find those two one-to-one correspondences. Now, these two are guaranteed to exist because remember, if a function is a one-to-one correspondence, it's guaranteed to have an inverse function. So that's why we know that nu inverse and epsilon inverse exist. Furthermore, we also have proven that if a function is a one-to-one correspondence, then so is its inverse. And that is how we know that these two not only exist, but are one-to-one correspondences. Now for transitivity. So given any graphs G, G prime, G double prime, and S, such that G is isomorphic to G prime and prime is isomorphic to G double prime, what we have to do is show that G is isomorphic to G double prime. Now we know that one-to-one correspondences are guaranteed to exist, so we say, okay, nu 1 is V of G to V of G prime, epsilon 1 is E of G to E of G prime. These are the two one-to-one correspondences guaranteed by the fact that G is isomorphic to G prime. Then nu 2 will be V of G prime to V of G double prime. Epsilon 2 will be from EG prime to G double prime. Those are the two one-to-one correspondences guaranteed to exist from the fact that G prime is isomorphic to G double prime. Well, then we can define two new functions. Nu, which is nu2 composited with nu1. This will be a function from V of G to V of G double prime. And epsilon, which is going to be epsilon sub 2 composed with epsilon sub 1. That is now a function E of G to E of G double prime. Furthermore, we have also proven that as long as the two functions you're composing are one-to-one correspondences, then the composition is a one-to-one correspondence. These two are one-to-one correspondences. Furthermore, they preserve the edge and point functions. So G is isomorphic to G prime. We have proven all three properties. So this is an equivalence relation, and the proof is complete. Now we say that a property P is called an invariant for graph isomorphism if and only if graphs G and G prime, this should be for all, if G has property P and G prime is isomorphic to G, then G prime has property P. So P is invariant if both G and G prime have the property, and they're isomorphic. So each of the following properties is an invariant for graph isomorphism, where n, m, and k are all non-negative integers. That is, if G and G prime are isomorphic, and G has any of these six properties, then so does G prime. First one has n vertices. Second one has m edges. Third one has n vertices of degree k. Fourth has a circuit of length k. Fifth has m simple circuits of length k. And finally, sixth is connected. And with that, this video on graph isomorphisms is concluded. In the next video, which is also the final video of the series, we will look at trees.